I'm going to be talking about JavaScript and Unicode and how the two go together. So first, let me introduce myself. This is me. I'm a web developer from Belgium, just like you guys. Well, most of the audience anyway. I recently joined the Opera developer relations team. And it's funny that I got Chrome socks, because Chrome socks is actually our company slogan. No, not really. I mean, no, actually, we do work on the Chromium project as well. So
you're not using Chrome.
Yeah, exactly. Anyway, in my spare time, I also like to collaborate on various open source projects. One of which is JSperf, which I made in 2010. Has anyone used JSperf? Let's do a show of hands. Okay, some people. Well, if you don't know what it is, it's just a website, and you can go there and you get this form. You can enter a few JavaScript snippets that are equivalent, so they do the same thing, but they're written in a different way. And then JSperf creates a test case for you that you can run in any browser that you care about, and it will tell you which snippet is faster and what the difference is. So it's really useful for performance testing in JavaScript. I'm also a member of the core dev team for the HTML5 boilerplate project, which is something you may have used. Can you hear me properly? Okay. So anyway, my Twitter handle is just my first name, Mathias. So if you happen to have any questions and you're too shy to ask them afterwards, just ping me on Twitter and I'll get back to you. Now, does anyone know who this guy is? Yeah, it's Jay-Z, of course, the famous rapper. But a little known fact about him is that at some point he decided to write a JavaScript program. So he installed Node and NPM and he started programming away. But at the end of the day, he had written a song about his frustrations with the language instead of writing a program. And actually, you may have heard this song before. It's called 99 Problems. Now, I'm making fun of JavaScript here, but don't get me wrong, I absolutely love the language. I think it's a great language. But just like with any other programming language, whenever you're writing code, it can happen that you're confused sometimes by a specific feature or behavior of the language. And this happens for all languages. For example, for PHP, there's even a dedicated website to these kinds of things called phpwhatthefuck.org. And we have the same thing for JavaScript, which is called whatthefuck.js. And it kind of collects these strange little nuggets of weird and surprising behavior in the language. Now, of course, all these things on these websites can perfectly be explained if you just look at the manual or read the specification or look at the implementation. But still, if a behavior in the language is confusing to a lot of people, then it's a bit of a problem, right? So that's why I'm going to go ahead and say that JavaScript, in my opinion, has a bit of a Unicode problem. And I'll show you why in a second. Now, why should you care about this? Because at this point you may be thinking, okay, this is probably going to be a talk about edge case issues that I will never have to deal with in my lifetime. But that's not true. Well, let's do a quick show of hands. Have you ever used JavaScript before? Okay, almost everyone is raising their hands. Keep them up, keep them up. Okay, drop your hand if you have never used a string in JavaScript before. Okay, nobody dropped their hands. Actually, some hands went up, which is weird. Okay, so have you ever used a string in JavaScript that came from user input or from a third-party API or any other source that you do not directly control? Yeah, well, still the same amount of hands. You can drop them now. But the point has been made. Whenever you want to support arbitrary input and arbitrary strings in your JavaScript application, there are some things that you need to do and that you need to keep in mind. And most of these things are, in my opinion, really surprising. So that's what this presentation is going to be about. Now, I started looking into this behavior a couple of years ago when I was working on a Punicode.js library. Does anyone know what Punicode is? I'll give you a hint. It has nothing to do with the Hulk making fun of your lame programming skills or anything like that. Unicode actually, well, traditionally, it was only possible to register domain names that had ASCII symbols in them. Like, you all know that you cannot use certain symbols in your domain name directly. And the entire web, in fact, has been built around this fact. And technically, even today, it's not possible to register a domain name that contains a special character, like a special Unicode character, for example. But Punicode is kind of like a workaround for that. So Punicode is an algorithm that converts an internationalized domain name, like the one you see there, mañana.com, to an ASCII-only representation. The same goes for cafe.be. If you actually register the domain name on the right-hand side, you will end up with the internationalized domain name on the left-hand side. So browsers automatically do this conversion for you. Yeah, that's actually a real domain name, poop.la. I wouldn't suggest going there, but it exists. Anyway, so all the browsers and all the other programs that need to deal with URLs have a Punicode encoder and a decoder built in. And basically, they just implement this algorithm. And that's what I wanted to write in JavaScript, just for fun. So that's Punicode. And I'm going to spare you the details of how the algorithm works exactly. But internally, at some point, I needed to loop over the internationalized domain name string and go over it character by character. And that sounds really simple, that part, but it's actually really hard, especially in JavaScript. And this presentation will explain why, and it will also explain how you do it properly. So for me, by working on this library, that's when I started to see all these issues in the JavaScript language. But before I get into all that, let's talk about Unicode itself, because there's a lot of misinformation about Unicode and what it really is. So first off, Unicode is not an encoding. It's actually much easier to think of Unicode as sort of a database that maps any symbol that you can think of to a number, a unique number for that symbol, and a unique canonical name for that symbol. So the whole point of this is that this way you can refer to any symbol without having to use the symbol itself, which is really useful. So for example, the Latin capital letter A, that's the canonical name for the symbol, has the code point U plus 0041. And the code points is usually formatted in this way. It starts with the U plus prefix, and then it's followed by some hexadecimal digits. And these are usually zero padded up to 4 digits, at least 4 digits. So another example is the Latin small letter A. Of course, this is a completely different symbol, so it has its own unique canonical name, and it has a completely different code point. So that's the basics of Unicode, really. I think you get the idea now. Each symbol simply gets its own Unicode code point. Now, there's a lot of weird symbols in Unicode, like the Unicode snowman, for example. This is a real character. I'm not sure why you would ever need this in your English text documents, but it's there if you want to use it. And the code point is U plus 2603. And then there's everyone's favorite Unicode character, the pile of poo. So I'm not making this up. This is actually the canonical name for a character in the Unicode standards. It's pile of poo. As you can see, the code point is 1F4A9, which consists of 5 hexadecimal digits. So at this point, you may be wondering, okay, how many code points are there? Or what's the highest possible code point value? Well, in Unicode, the code point values range from 0 to 10FFFF. So that's over 1.1 million possible symbols. Now, not all of these code points have been assigned a symbol yet in Unicode, but this range has been reserved so that in the future, whenever they want to add a new symbol, they can just pick any of those code points that haven't been already used and just assign the symbol there. Now, to keep things organized, Unicode divides all these things, all these code points, into 17 planes that consist of about 65,000 code points and there's 65,000 symbols for each plane. And the first of these planes is probably the most important one. It's called the Basic Multilingual Plane, or the BMP, and it contains all the most commonly used symbols. So whenever you're writing a text document in English or even in Spanish or French or whatever, chances are that you won't need any characters or any code points outside of the BMP. And just like any other plane, as you can see, it's about 65,000 symbols in there. And then there's a group name for all the other planes combined as well. They're called the supplementary planes or the astral planes. So code points within that plane are called astral code points or astral symbols. You get the idea. Now, these astral symbols are pretty easy to recognize because if you need more than 4 hexadecimal digits just to represent them, that means it's an astral symbol. Okay, so that's all you need to know about Unicode to deal with strings in JavaScript correctly. So let's move on to the JavaScript behavior that I was talking about. So now that you have a basic understanding of Unicode, it's easy to see how it applies to JavaScript strings. For example, you may have seen stuff like this before. It's in a string, you can have a backslash followed by x and then followed by 2 hexadecimal digits. And this is called hexadecimal escape sequence. Now, in this case, it gives you a way to refer to a Unicode code point. That's what the digits refer to. So it's a way to refer to a symbol without using the symbol itself. So in this case, this is just a string ABC in caps, but represented using escape sequences. Now, this is useful in some cases, but it's a bit limited in its use because we're limited to just 2 hexadecimal digits. So we can only use this for the code points in the range from O to FF. Now, what's a bit more useful is the so-called Unicode escape sequence. It starts with a backslash followed by U and then followed by 4 hexadecimal digits instead of 2. So this gives you a much bigger range of code points that you can escape this way. So again, this is the same string, ABC, but now that you have 4 hexadecimal digits to use, you can also escape characters like U plus 2661, which is the Unicode white heart symbol, which looks like this. So using this type of escape sequence, you can actually escape all the characters in the BMP, in the basic multilingual plane, which is useful. But as you know, there's still these 16 other planes, the astral planes. So what do we do about those? We cannot represent them using just 4 hexadecimal digits because we need more than 4 digits. So what about those astral code points? Or another way to phrase the question, what about the pile of poo? And other equally important astral symbols, of course. So remember, there's over 1 million of these astral symbols in total. And the answer is, well, we can actually represent them using escape sequences, but it's a bit complicated. In ECMAScript 6, the upcoming version of JavaScript, this will actually be really easy because you can just use the Unicode code point escapes. These are new, and they start with a backslash followed by U, followed by braces. And then between those braces, you can use up to 6 hexadecimal digits. So that is enough to represent all possible Unicode code points. So this is really useful, and as you can see, you can just escape the pile of poo by using its code point, and then you get the correct string that you would expect. Sorry for the beatboxing there. Okay. Now, for backwards compatibility with ECMAScript 5, so for existing implementations, you actually need to use surrogate pairs. So if you want to represent a pile of poo using escape sequences today, you actually need 2 separate escape sequences, which is a bit confusing, especially because the code points for these escape sequences are probably not what you would expect. They don't look anything like the original code point. So in this case, for these surrogate pairs, each surrogate represents the half of the symbol, and it's only when they're combined together they form a single symbol. And there are formulas that can be used to calculate these surrogate halves based on an astral code point, and the other way around, you can go back to. And this is a JavaScript implementation of those formulas. You don't really need to look into it too much, but again, this is something that you need to keep in mind whenever you're dealing with strings in JavaScript, because often you will need to use these surrogate pairs yourself, and sometimes you will even have to calculate them yourself using this code. Now, this whole concept of using just a single escape sequence for BMP symbols, but then using 2 separate escape sequences for astral symbols is really confusing. And it has lots of annoying consequences in the entire JavaScript language. So let's say, for example, that you want to count the number of characters in a string. It sounds fairly simple, right? Well, my first thought would be to use the length property that any string has. So for example, if you have a string with the capital letter A in there, with the code point 41, you can tell that the length is just 1, right? And this can be explained by using escape sequences. If you represent a string using nothing but escapes, you see that there's only a single escape sequence needed to represent it. So it makes sense that the result is 1. The same goes for the capital letter B. But what's important here is that this is not always the case. The length property of a string does not always reflect the number of symbols or code points in the string. For example, let's try some slightly different characters. They even look a bit similar. These are the mathematical bold capital A symbol in Unicode with the code point 1D400 and the mathematical bold capital B. And as you can see, they have a length of 2 instead of 1, even though there's only 1 symbol there in the string. I thought it was really confusing behavior. But it can be explained because if you need to represent it using nothing but escape sequences, you can see that there's 2 escapes needed for the one symbol. Of course, this is really, really confusing because we're just humans, and we generally think in terms of Unicode characters rather than in surrogate halves or anything. No one thinks like that, only computers do. Now, similarly, if you try to wrap the pile of poo in a string and then get its length, you will get 2, the number 2. And there's a very obvious joke to be made here, but I'm just going to skip ahead. So here's a practical example of where this causes issues. This is a screencast that I made on the Twitter website once upon a time. As you can see, they have this character counter at the bottom that tells you how many characters you have left. And in their backend, they do the right thing. And if you use an ASCII symbol or any other symbol, they don't care. It just counts as a single symbol. However, in their front end, they had a bug. They would just use the length of the string and do the calculation based on that. So as you can see here, for each pile of poo you enter, the number decreases by 2 instead of 1. So while this bug was there, you could only post tweets with 70 piles of poo in them instead of 140. Yeah. Now, luckily they fixed the bug since. But another example is the countable JS library, which you may have seen before. Basically what it does is you hook it up to a text area or an input on an HTML page, and then it will count the number of characters and paragraphs and words that you enter into there. And then it will list those numbers elsewhere on the page. That's all it does, really. So the first thing I did when I saw this demo page for the project was to enter a pile of poo, of course. And unsurprisingly, it counted as 2 characters rather than just 1. Now, I reported the bug and it has since been fixed, but the bottom line is this is a really easy mistake to make. But if you're writing a JavaScript library or you're doing anything in JavaScript that involves strings, especially when you don't control the input yourself, you have to make it work with all kinds of symbols. You just don't have a choice. You have to. So consider ASCII symbols and not just the symbols in the basic multilingual plane. And really the easiest way to verify this is just to test it with some ASCII symbols like I did here. Just throw some piles of poo in there and see what happens. So getting back to our question, how can we accurately count the number of symbols in a JavaScript string? You can use something like this. So getting back to my Punicode JS library, this is not its main functionality. The main functionality is to convert between the different domain names. But to iterate over the internationalized domain names symbol by symbol, I had to implement some helper methods that would do this and that would account for surrogate pairs. And I decided to expose those methods so that other people can use them in their own code. So in this case, you can use punicode.ucs2.decode. You pass in a string, and it will return an array of Unicode code points. So it will have only 1 item for each code point in the string. So then if you get the length property of the resulting array, instead of on the string directly, it will get a more accurate result. One more note, the Punicode JS library that I was talking about, it's included with Node.js by default. So if you want to use it in Node, you don't have to install anything, just require it, require Punicode, and you get going with that. So in ECMAScript 6, this will be much easier, and you won't need a library for it anymore. You can just use array.from. You pass in a string there, and then it will create an array containing a string for each symbol in the string. So this is similar to the previous solution. In the background, this uses the string iterator that is also new in ECMAScript 6, and this string iterator is defined so that it only loops over whole symbols. So it automatically takes care of these surrogate pairs for you. And as you can see, the result is much more accurate this way. I've also created a tool that takes a string as input and then shows the escape sequences for any special characters within that string. So it's a bit similar to a hex dump, except the output is valid JavaScript, which is sometimes more useful. And with this tool, it's really easy to tell what kind of Unicode symbols the string contains, even if the symbols are non-printable or just whitespace symbols, as you can see here. Now, if we're being pedantic, and this depends on your use case, of course, it's actually a bit more complicated. So now we know how to count code points correctly. But sometimes, a string looks visually like it contains a number of symbols, while in reality it contains more symbols. So how can we account for stuff like that? For example, in this case, JavaScript seems to be telling us that these strings are different, but they look the same to us, right? So what's going on here? Well, to tell you what I did, I took these two strings and I pasted them into the tool that I just showed you, and then it gave me these results. So as you can see, the first string contains the character f1, which is an n with a tilde on top of it. And then the second string is different. It has a separate n character, and then followed by the character with code point 0303, which is a combining tilde. And a combining mark always gets applied to the previous symbol. So visually, they look exactly the same, but if you look at it this way, it's obvious that they're not the same string. The first string has a length of 6, the other has a length of 7, and they use different symbols, so there's no way that they can be the same. So how can we fix our solution so that it even accounts for this sort of thing, for these look-alike symbols? In this case, if you want to get the length of the string, we probably expect the result of 6 for both strings, right? Well, in ECMAScript 6, this will be really easy because it introduces Unicode normalization. You can just call the normalize method on any string and then pass the normalization form in there. And this, as a result, will take care of most look-alike symbols like the one we've seen earlier. And then after that, of course, you still have to account for astral symbols and surrogate pairs like we did before. And you can actually use this today in Chrome and Opera. This is already landed. But if you want it to support other browsers as well, which you should do, you can use a polyfill called unorm. The link is there at the bottom. I'll also put the slides online afterwards. And this is a completely spec-compliant polyfill for the normalize method. Now, still, this is not exactly perfect, just like your ringtone. Now, for example, if you have a string like this, well, I count 9 characters here. But if you feed it to the function that we just created, you'll still get a result of 116, even with our pedantic version of the function. So this is probably not what you expected, but if you need to support stuff like this, you can solve it by using a regular expression that takes care of all the combining marks and the grapheme extenders. You can basically just remove them from the string and then count the number of code points just like we did before, and that would give you a better result. But I'm not going to show you the regular expression here because it would scare you and you would start bleeding from your eyes and stuff like that. I've seen it happen before. It wasn't pretty. Now, another example is reversing a string in JavaScript. It sounds really simple, and in fact, the most common solution to this problem looks like this. You just take a string, you split it into an array of symbols, then you reverse that array, and then you join it back together into a string. And this works fine for a lot of cases. For example, if you have the string ABC, it reverses into CBA, which makes sense. Now let's try another one. If you take the string mañana with the n with the tilde on top of it, it still reverses correctly. Now let's try the other mañana where the n and the tilde are 2 separate characters. In this case, the combining tilde now gets applied to the wrong character. It gets applied to the A instead of the n, which is probably not what you would expect. And then finally, let's try to reverse a pile of poo or any other astral symbol. And the result here is that you will get the surrogate halves, but in the wrong order. So the pair is now in the wrong order, and this means that you basically lost some data there. The string won't be really usable. So this is probably not what you would expect, and you somehow need to work around these issues. Now, luckily for us, a brilliant computer scientist named Missy Elliott came up with a bulletproof algorithm that accounts for these issues. And the algorithm goes, I put my thing down, flip it, and reverse it. And indeed, by first swapping the position of the combining marks with their original characters, and then also reversing any surrogate pairs before further processing the string, the issues are avoided successfully. So thank you, Missy. And I actually wrote a JavaScript implementation of her algorithm called srever. So if you ever need to reverse a string in JavaScript, you can just use that. And as you can see, it will account for these issues correctly. Now, this behavior affects other string methods too. It's everywhere in the JavaScript language. So for example, if you try to use string.fromCharacter code, this is a function you can pass in a code point, and it will turn that code point into a string containing that symbol for that code point, which is really useful. But it only works the way you would expect it to for BMP code points. If you pass it an astral code point, it will still give you a result, but it probably is not going to be the result that you would expect. So this function is slightly broken. It only works for BMP characters. Now, the solution here is to use surrogate pairs. And in this case, you would have to calculate the code points for the surrogates yourself, which is a pain, of course. What you could also do is use another library, like, for example, Punicode JS, which has a helper method where you can just pass in an array of code points, and then it will do the conversion for you. That's slightly easier because you don't have to calculate it again anymore. But what would be even better is the new function that is coming in ECMAScript 6. It's called string.fromCodePoint. And it's pretty much exactly the same as string.fromCharacterCode, except that this one actually works, not just for code points in the BMP, but for any code point. And you can actually use this today if you want to by using the polyfill that I'm linking to at the bottom. Now, another method is string.prototype.characterAdd. It is similarly affected by this behavior. So if you use characterAdd to retrieve the first symbol in the string containing the pile of poo symbol, you won't get the entire pile of poo, you just get the first surrogate half. So you get half the pile of poo, which sounds like a good thing, but actually it's not what you want. Now, this can be fixed in ECMAScript 7, not in ECMAScript 6. This is a proposal that I wrote, string.prototype.add, and it would allow you to get the symbol at a given position, and it would automatically account for these surrogate halves and combine them together for you. Another example is string.prototype.characterCodeAdd, which has a similar problem. If you use it to retrieve the code point of the first character in the string with the pile of poo, you would only get the code point for the first surrogate half, not the entire character. Again, this is really confusing. Now, ECMAScript 6 fixes this by introducing yet another method, which magically does the same thing, but it works correctly even for astral symbols. Now, another fun thought exercise is how do you iterate over all symbols in a string? Now, you may remember that I needed to do this for the Punicode JS library. So the thing to keep in mind here is that we need to account for astral symbols. And in ECMAScript 5, this looks something like this. And this is actually a simplified solution. It's not perfect. You actually need more code than this, which is terrible enough already. So you need a lot of boilerplate just to account for those annoying surrogate pairs and to combining back together into a single character. Now in ECMAScript 6, it will be much easier because you can just use the string iterator. You can use for_of to iterate over each symbol in the string, and it will automatically take care of the surrogate pairs for you. It's much cleaner. Now, I didn't mention all the string methods one by one, but string.prototype.substring or slice or basically anything else involving strings in JavaScript has similar issues, so look out when you're using them. Now, another fun thing to think about is regular expressions. For example, the dot operator in a regular expression only matches a single character, but because JavaScript considers surrogate halves to be separate characters, it would never match an astral symbol. So in this case, you might expect the regular expression to match and the result to be true, but instead it's false, because the pile of poo consists of two surrogate halves as far as JavaScript is concerned. So let's think about this for a second. What kind of regular expression could we use to match any Unicode code points? Well, we cannot use the dot operator as we've demonstrated. Besides, it wouldn't match line breaks either. If you wanted to match line breaks, we can solve that problem by just using this sort of regular expression where we basically match all the white space characters and then match all the non-white space characters as well. And then that matches any character. But still, it would only match characters in the JavaScript definition of the words, so only surrogate halves. It wouldn't match astral symbols. So does anyone know or have any idea what the regular expression to match any Unicode symbol would look like? Okay, it will look something like this. Yeah, my thoughts exactly. So what's happening here is that the first part of the regular expression matches any BMP symbols that don't start a surrogate pair. Then the second half of the regular expression matches a surrogate pair, so an astral symbol. Now, of course, this is not the type of regular expression that you want to be writing by hand, let alone debugging it. That would be crazy. So what I did is I used a JavaScript library called Regenerate to create this regular expression for me dynamically. And it looks something like this. So you create a new Regenerate instance, you define the range. In this case, I just add the range of all Unicode code points. And then I call the toString method on it, and then it will return a string that represents a part of a regular expression that I can use. It returns a string because it's supposed to be used as part of a build script, so you can dynamically insert the resulting regular expression into a JavaScript file and use it from there. Now, another slightly more advanced example would be to create a new regenerate instance, add all the possible Unicode code points, and then remove a range of symbols, in this case all symbols from A to Z, then remove a single symbol, in this case the pile of poo, and then create a regular expression that matches all those characters in the set. And then it would look something like this. So again, this is not the type of regular expression that I would like to write by hand, let alone debug it. So if I have the choice between maintaining the regular expression directly or by just maintaining those 5 lines of code right above there, I definitely know what to choose. So the whole point of this library is to just create a build script that generates these complex regular expressions for you, and that way it's much, much more maintainable. Now, getting back to our problem, it can also be solved in ECMAScript 6 by using the new regular expression U flag. In that case, if you use this U flag, the dot operator will match whole code points instead of just surrogate halves. So this magically fixes the behavior that you were after. Another example is character classes in regular expressions. For example, if you do A to C in a character class, you probably expect it to match A, B, and C, right? Well, similarly, if you create a character class with ASCII symbols, you would expect it to match all the symbols within that range. But this is not exactly true. This doesn't work the way you would expect it to. In fact, as soon as you execute the first line of JavaScript there, it will throw a syntax error, because in this case, it will say the range is out of order in the character class. So what is going on there? Well, as far as JavaScript is concerned, this regular expression looks like this, because each ASCII symbol consists of 2 separate characters, right? So what JavaScript is trying to do here is to create a range between those 2 characters, between the last surrogate for the first symbol and the first surrogate for the second symbol, which is not what you want. And it's also impossible because the range is in the wrong order. So even if it would work, it wouldn't do what you want. So the way to fix this in ECMAScript 6 is, again, just introduce the U flag, and then it magically starts working the way you would expect it to. However, if you need a solution that works today, you're back to using a tool like Regenerate, for example. So you just say Regenerate, and then you add the range that you want, and then you turn that into a regular expression, and it will look completely weird, like the one here, but it will work the way you would expect it to, and it will match only the symbols that you defined. So in summary, I think it's fair to say that JavaScript has a Unicode problem, but rather than complain about it like Jay-Z did, I think we should be doing more of this instead. Yeah, we should just deal with it and really work around these issues, because once you're aware of them, which you all are now, it's not really that hard to work around them. And remember the pile of poo test. I think this is really important. So whenever you're working on a JavaScript library or you're using a JavaScript library and you're looking through their unit tests and you see that there's no pile of poo in there, just submit a pull request with a pile of poo, and it will really help them. So thanks, that's it for me. The slides can be found there.
Time for some questions. We don't have another mic.
Yeah, you could, for example, use Regenerate to create a regular expression that only matches ASCII symbols. And then you can apply that regular expression to the string, see if it matches. If it matches, then you know you have to do some extra work. That would work. Yes? Yeah, exactly.
Can you repeat the question?
Yeah, so the question was, why do they introduce new methods in ECMAScript 6 rather than, wow, that would be a fun language. So rather than fixing the old ones that are broken. Well, the problem is backwards compatibility. There's a lot of existing code on the internet today that relies on the broken behavior of these functions. And if we were to magically fix them, all those scripts would suddenly be broken. And that's something we just cannot do. We cannot break the web. So instead, we have to introduce new methods. Good question. Yeah.
Do you think the JavaScript?
No. For the same reason, we're practically stuck with them forever, because there's so much existing content that just relies on these things. Yeah. his point was that the old functions could be useful if you want to know the exact amount of bytes that the string consists of. And that really depends on the encoding that you're going to store the string in. JavaScript uses UCS2 internally, which is also what DOM strings use, so browsers use that internally too. But if you're going to save a string as UTF-8, for example, it will be a different number of bytes for each string, depending on the characters that you use. So it all depends. I don't think the old functions are all that useful, to be honest, but for a long time we just didn't have anything else. Yes? Yeah, so there's a lot of different encodings, UTF-8, UTF-16, UCS2, which is what JavaScript uses internally, which is why we're having this behavior. Well, for most purposes, UTF-8 is probably the best encoding to use because it's optimized. For example, if you use a BMP symbol, it will take 1 to 3 bytes only. And only if you use an ASCII symbol, which are not that common, honestly, then it will take up 4 bytes. So it's a variable length encoding, which is really useful. On the other hand, if you use UTF-16, as you can see here, you have either like 2 bytes or 4 bytes that are needed, which is not as useful because a lot of, well, the most common characters are BMP symbols. So for BMP symbols, they would take up twice as much storage space as UTF-8 would. So it depends, but for most things, I would say use UTF-8 when you can. Actually, I have an entire blog post that goes on between the difference between UCS2 and UTF-16, and the end result is that JavaScript is more close to UCS2 than it is to UTF-16, because in UTF-16 you cannot have lone circuits, and JavaScript allows those, and there's some other reasons as well. But I'm happy to discuss this after, over a beer or something. Yeah. Well, for the examples that I showed in my slides, double equality versus triple equality didn't really matter because they were always of the same type. In general, I tend to use double equals rather than triple equals. I know that's an uncontroversial move on my end, but I'm of the opinion that if you know that the types are going to be exactly the same, there's just no point in using triple equals. Like for example, if you use typeof and then a variable, you know that it will always return a string. So in that case, I think it's useless to use triple equals. But that's personal preference, really. Yeah.
Well, thank you so much,
let's have some beers.